long as humans have existed, we have asked one question that refuses to leave us in peace. Where did everything come from? Not just the trees outside our window, the stars above our head, or the ground beneath our feet, but everything: time, space, matter, energy, the rules of nature themselves. It is the oldest question, the most stubborn mystery, and the one puzzle that unites every culture, every civilization, every curious mind. This is the question Stephen Hawking spent his life chasing. Before Hawking became the name the world knows, before the machines that helped him speak, before the fame and the theories and the equations, he was simply a young man staring at the sky, certain that the universe was hiding a story, and he wanted to read it. In this journey, we will walk through that story, not as scientists locked inside formulas, not as students memorizing definitions, but as explorers, trying to understand the universe the way Hawking wanted everyone to understand it, clearly, simply, and with wonder. So let us begin from the beginning, or more accurately, from the moment before the beginning. A moment so strange that even time itself did not exist. For a long period in history, people explained the universe using myths, powerful gods, cosmic battles, and magical creation stories. These stories were meaningful, but they could not predict eclipses, measure the stars, or explain why nature followed such precise rules. Slowly, human beings shifted from myth to observation, from imagination to measurement, from belief to science. The first scientists, thousands of years ago, looked at the sky and saw patterns. Stars rising and setting in repeatable cycles, seasons changing in predictable rhythms. They wondered, does the universe run on rules? If so, can we find them? This curiosity sparked the scientific spirit that later helped Hawking understand the origins of time. But the universe was not ready to give away its secrets easily. For centuries, people believed Earth sat at the center of everything. It felt obvious. The ground did not move beneath our feet. The sky revolved around us. Humans assumed we were the point around which all creation rotated. Then came a revolution of thought. First Copernicus, then Galileo, then Kepler showed that Earth was not the center at all. It was one planet among many, orbiting a sun that was merely one star among billions. The universe suddenly became large, too large, almost frighteningly large. But this expansion of our understanding was necessary. The journey from Earth to stars, from stars to galaxies, and from galaxies to the universe led scientists to one conclusion: everything we see today must have had a beginning. And this is where Stephen Hawking entered the picture, taking the ancient question, where did we come from, and pushing it further. How did the universe begin? Why does it obey such strict laws? Who set the clock of time ticking? And was there ever a moment when the clock was not ticking? To understand Hawking's answers, we must first understand how the universe behaves. And that starts with one of the greatest scientific revolutions in history, Einstein's theory of relativity. Einstein discovered that time and space are not separate things. They are woven together like threads in a cosmic fabric. When heavy objects like stars and planets sit on this fabric, they bend it, twist it, stretch it. This bending is what we feel as gravity. We do not fall toward Earth because Earth pulls us downward. We fall because space itself curves, guiding us like a river guides a boat. This was a stunning idea. It changed every rule of physics, and it opened a door for Hawking, who built on Einstein's foundation to explore the most extreme places in the universe, places where space bends so much that even light cannot escape. Black holes. To most people, black holes sound like monsters of the cosmos. Dark, hungry, mysterious. But to Hawking, they were the key to understanding creation itself. Black holes are what happen when mass becomes so dense that space collapses inward. Imagine squeezing a mountain into the size of a pebble. The density becomes unimaginable, the gravity unstoppable. At the center of a black hole lies what physicists call a singularity, a point where the laws of physics as we know them break down. This mattered to Hawking because singularities reveal the limits of our understanding. If we want to know where the universe came from, we need to understand what happens to matter, energy, and time when they reach extremes. A black hole is the perfect laboratory for that. But before Hawking changed the world's understanding of black holes, scientists believed something else. That black holes were simple objects. They swallowed everything. They released nothing. They contained no information, no structure, no clues. They were the universe's trash bins. Hawking refused to accept this. He believed nature did not waste information. And if information could not be destroyed, perhaps black holes were not so simple after all. This line of thinking led him to one of the most remarkable discoveries in modern physics: Hawking radiation. The idea that black holes are not perfectly black. They slowly leak heat, slowly shrink, slowly evaporate. In other words, even the darkest places in the universe are not eternal. But before we reach this discovery in our journey, we must step back and understand how scientists first figured out the age and beginning of the universe. For most of history, people assumed the universe had always existed, eternal, unchanging, infinite. Then in the early 20th century, astronomer Edwin Hubble made an observation that shocked the world. He studied distant galaxies and discovered they were moving away from us, not randomly, but in a pattern. The farther the galaxy, the faster it moved. This meant one thing: the universe was expanding. If it is expanding now, then in the past it must have been smaller. If we reverse the expansion, the universe shrinks more, shrinks further, until finally, everything we see, stars, planets, galaxies, light, energy, even space itself, collapses into a single, unimaginably dense point. This point is the beginning of our universe, what scientists later named the Big Bang. The Big Bang was not an explosion in space. It was the explosion of space, the birth of time, the moment when the cosmic clock first started ticking. But what existed before that moment? What caused it? Why did the universe begin at all? These were the questions Hawking dared to explore. He argued that before the Big Bang may not even be a meaningful idea. If time itself began at the Big Bang, asking what happened before is like asking what lies north of the North Pole. The question itself may not make sense. Instead, Hawking suggested something revolutionary: that the universe might have no boundary, no edge, no beginning in the traditional sense. That the universe could be finite, but unbounded, much like the surface of a sphere, has no edge yet is not infinite. To understand how time behaves in the deepest parts of the universe, Hawking introduced the idea of imaginary time, a mathematical way of smoothing out the sharp edges of the Big Bang, making the universe self-contained. Imagine time not as a line with a start and end, but as a loop, a smooth curve, a surface with no beginning. This idea does not eliminate the Big Bang, but it gives us a new way of understanding it, a way that removes the need for a creator in scientific terms, a universe that builds itself through natural laws. But Hawking's goal was not to remove meaning from life. Quite the opposite. He believed that the more we understand the universe, the more we understand our place in it. that science does not destroy wonder, it expands it. He wanted people to see the universe not as a cold, distant machine, but as a story we are all a part of. A story written in light, space, time, and curiosity. And so, as we continue this journey, we will explore how the universe cooled, how atoms formed, how stars ignited, how galaxies shaped, and how all of it ultimately led to us tiny beings on a small planet, trying to understand a cosmos wider than imagination. This is only the beginning of the story. Hawking spent decades uniting the biggest ideas in physics, relativity, quantum theory, cosmology, into a single narrative. And our journey into that narrative has only begun. After the Big Bang, the universe was a seething, hot soup of particles, a place where matter and energy danced in a chaotic, unstructured symphony. For the first few moments, temperatures soared unimaginably high. Protons and neutrons collided, quarks combined and split, photons bounced endlessly, and time itself seemed to pulse with the rhythm of creation. Gradually, the universe expanded and cooled. Particles began to form the first atoms. Hydrogen, helium, and traces of lithium became the building blocks for the cosmos. In these simple elements lay the seeds of all complexity, the potential for stars, planets, and ultimately, life. Gravity, the silent sculptor of the universe, began its work. It gathered hydrogen into dense clouds, drawing matter together to ignite the first stars. These early stars burned brilliantly, fusing hydrogen into helium, then into heavier elements, carbon, oxygen, iron, essential ingredients for planets and life. In a way, every atom in our bodies was forged in the heart of a star that lived and died billions of years ago. Hawking often reminded us that the universe is not static. It evolves. Stars are born, they live, they die. Galaxies form, collide, and reshape themselves. And hidden in this cosmic dance are the laws of physics that govern every motion. Hawking's fascination was not merely with the stars themselves, but with the rules that allowed stars to exist at all. While galaxies swirled and stars blazed, humans on Earth were beginning their own journey of discovery. For centuries we had observed the skies, but our understanding was limited. Gravity was a mystery, motion was misunderstood. Time seemed absolute, flowing uniformly for everyone. And yet, as humanity studied the heavens, the rules began to emerge. Isaac Newton codified the laws of motion and universal gravitation. For the first time, humans could predict planetary motions with astonishing accuracy. The universe became a clockwork machine, elegant and deterministic. Newton's equations explained how planets orbited, how tides shifted, and even how projectiles traveled through the air. Yet, even Newton sensed that the universe held deeper mysteries. Why did space exist at all? What set the constants of nature? How did matter emerge? These questions would linger for centuries, leading eventually to the revolutionary ideas of Albert Einstein. Einstein introduced a profound shift in our understanding. Time was no longer an absolute backdrop. Space and time were intertwined into a single entity, space-time. Gravity was not a force acting at a distance, but a curvature of space-time caused by mass and energy. This insight allowed scientists to comprehend black holes, the bending of light by massive objects, and the dynamics of an expanding universe. Hawking's genius was in taking Einstein's equations and exploring the extreme consequences. He asked, what happens at the singularity of a black hole? What happens to time at the beginning of the universe? These were not idle speculations. They were questions about the very fabric of reality. As the universe cooled further, matter clumped into galaxies. The Milky Way formed. a vast collection of stars, gas, and dark matter held together by gravity. Within this galaxy, our sun emerged, a star perfectly positioned to sustain life on a small blue planet we call Earth. On Earth, life began quietly. Single-celled organisms evolved in water, eventually giving rise to complex life forms. Evolution sculpted the diversity of life, and intelligence emerged. Humans developed consciousness, language, curiosity. They began asking the very questions that would lead to modern science. What is the universe? How did it begin? What are we? Hawking often emphasized the interplay between the cosmos and human thought. Our understanding of space-time, black holes, and the universe's beginning is inseparable from our human perspective. We observe, measure, theorize, and in doing so, we become participants in the universe's story. But the universe is not just vast, it is strange. Quantum mechanics revealed that at the tiniest scales, reality is probabilistic. Particles appear and disappear, exist in multiple states simultaneously, and influence one another in ways that defy classical intuition. Einstein himself was uneasy with these ideas, famously declaring that God does not play dice with the universe. Hawking, however, embraced the paradox, recognizing that the probabilistic nature of quantum mechanics is not a flaw, but a fundamental truth. It is here that Hawking's insight into black holes became revolutionary. If black holes can emit radiation, a phenomenon now known as Hawking radiation, then information about the matter that falls into them is not lost. The universe, even in its darkest corners, preserves its story. Meanwhile, cosmology matured into a precise science. Observations of the cosmic microwave background revealed the universe's earliest light, a remnant of the hot, dense state immediately after the Big Bang. Large telescopes mapped galaxies across billions of light years, confirming the predictions of expansion. The discovery of dark matter and dark energy added new chapters to the story, mysteries yet unresolved, inviting generations of scientists to continue the journey. Hawking's message was clear: the universe is comprehensible. Through observation, mathematics, and reasoning, humans can uncover the secrets of existence. Knowledge is not just for scientists, it is for anyone willing to wonder, to question, to explore. As we consider the cosmos, from atoms to galaxies, from quarks to black holes, we see patterns, laws, and structure, but we also see the unknown. For every answer, there is a deeper question. Every discovery opens new horizons, and this is precisely what Hawking wanted us to understand, that curiosity is infinite, and the universe is vast beyond imagination. In the next part, we will explore the mind-bending concept of time itself, the singularities at the heart of black holes, and Hawking's daring theories about the origin and fate of the universe. We will follow his reasoning step by step, unraveling concepts that challenge even the brightest minds, yet presenting them in a way that is accessible, engaging, and unforgettable. Time is the river in which we float, the invisible current that carries us from birth to death. Yet for centuries, humans assumed time was uniform and absolute. Every second ticked identically for everyone, everywhere. This belief guided Newtonian physics, everyday life, and our perception of reality. But the universe has a way of proving assumptions wrong. Einstein's theory of relativity shattered the notion of absolute time. Time stretches and contracts depending on speed and gravity. A clock near a massive object runs slower than one far away. Time is not a universal constant. It is a flexible dimension, intertwined with space. Hawking recognized that to understand the universe, one must understand time itself. And so, he turned his attention to one of the most extreme manifestations of time: black holes. These cosmic monsters are not merely massive. They are regions where gravity is so intense that space-time curves infinitely. At their heart lies a singularity, a point where densities and curvatures become infinite, and the laws of physics as we know them break down. Space, time, and matter converge into an enigma. For decades, black holes were considered inescapable. Anything that crossed the event horizon, the invisible boundary, would be lost forever. The universe, it seemed, hid its secrets behind these dark veils. Yet Hawking's brilliance lay in questioning assumptions. Could information truly disappear? Could the universe destroy what it had created? Through complex mathematical reasoning, Hawking demonstrated that black holes are not perfectly black. They emit radiation. They leak energy. Slowly, imperceptibly, they evaporate. Hawking radiation transformed our understanding. Black holes became laboratories for the most profound questions. How does information survive? How does quantum mechanics interact with gravity? How did the universe begin, and how might it end? These revelations brought new clarity to cosmology. If black holes obey physical laws and preserve information, then the universe itself is subject to elegant, predictable principles, even in its most extreme conditions. Hawking's work bridged the cosmic and the quantum, showing that the microcosm and macrocosm are deeply interconnected. Time itself became a focus of curiosity. Hawking proposed a revolutionary idea, the no-boundary proposal. In this model, the universe does not have a singular starting point in a traditional sense. There is no beginning in time as we understand it. Instead, time behaves like another dimension of space in its earliest state, forming a smooth, self-contained surface. The universe is finite but unbounded, without edges, without a first moment in the conventional sense. This idea is difficult to grasp. Imagine standing on the surface of a globe. There is no edge to fall off. You can walk in any direction, and eventually you return to your starting point. Hawking suggested that the universe's space-time is similar, continuous, smooth, and self-contained. Asking what came before the universe may be meaningless because time itself began with the universe. Beyond the beginning, Hawking considered the fate of the universe. Observations of distant galaxies revealed that the universe is expanding, a discovery made by Edwin Hubble. The expansion is not slowing, it is accelerating, driven by a mysterious force called dark energy. The ultimate destiny of the cosmos could be an eternal expansion, a gradual fading of stars and galaxies, or a dramatic collapse back into a singularity, a cosmic cycle that begins and ends with extremes beyond comprehension. Throughout his life, Hawking emphasized that understanding the universe does not strip life of wonder. On the contrary, it deepens our sense of awe. The vastness of space, the curvature of time, the formation of stars, and the delicate balance of forces that allow life to exist, all are miracles governed by natural laws. Knowledge enhances our appreciation for existence. Black holes, singularities, and the early universe are not just abstract concepts. They are the key to understanding ourselves. Hawking's exploration of the cosmos invites us to see our place in the universe, tiny yet capable of immense understanding, limited yet capable of creativity, fragile yet able to comprehend the grandest scales. In studying time, Hawking showed that science and imagination are intertwined. We use mathematics, observations, and logical reasoning to describe the universe. But understanding requires wonder, curiosity, and a willingness to think beyond everyday experience. The universe is stranger than we can imagine, and our role is to explore, to question, to illuminate. Hawking's life itself was a testament to resilience and determination. Diagnosed with a degenerative motor neuron disease, he defied expectations for decades, continuing to work, teach, and communicate complex ideas with clarity and humor. His disability became part of the story of human perseverance, showing that physical limitations do not confine intellectual curiosity. By the end of his life, Hawking had unified enormous ideas into a narrative accessible to millions. He showed that black holes are not monsters, but messengers. That time is not absolute, but dynamic. That the universe is comprehensible, yet mysterious. He made science personal, showing that our quest to understand the cosmos is also a quest to understand ourselves. In the next part of this journey, we will explore the most mind-bending concepts: quantum mechanics in the cosmos, the interplay between uncertainty and determinism, and the final frontiers of modern physics. We will see how Hawking's ideas continue to inspire physicists, cosmologists, and anyone who dares to ask the biggest questions. Oh, the universe is not only vast, it is strange. At the tiniest scales, reality behaves in ways that defy intuition. Particles can exist in multiple states at once, appear and disappear without cause, and influence one another across space instantly. This is the domain of quantum mechanics, and it is here that Stephen Hawking found both mystery and opportunity. Also, quantum mechanics, though strange, is fundamental. It governs the behavior of everything: the atoms in your body, the stars in the sky, the energy that binds galaxies. Hawking understood that any complete description of the universe must account for both the vastness of space-time and the peculiarities of the quantum realm. Only by bridging the infinitely large with the infinitely small could the story of the cosmos be told. This quest brought Hawking to the heart of black holes. Previously thought to trap everything forever, black holes, according to quantum theory, are not completely black. Tiny fluctuations at their edges allow them to emit radiation, now famously called Hawking radiation. This means that even in the darkest corners of the universe, the laws of physics are in play, information is preserved, and the universe's story continues to unfold. Hawking's insight resolved one of the greatest paradoxes in physics. If black holes destroyed information, the universe's laws would break down. By showing that information can escape, he demonstrated the consistency of the cosmos. The universe, even in its most extreme conditions, obeys rules that are discoverable, understandable, and elegant. While black holes embody the extremes of gravity and time, quantum mechanics reminds us that uncertainty is also fundamental. At subatomic scales, outcomes are probabilistic. We can predict tendencies, probabilities, and patterns, but not exact futures. This is not a limitation. It is the fabric of reality itself. The universe is orderly and unpredictable at the same time. Hawking's genius was in combining these realms, the cosmos of stars and galaxies, and the quantum world of particles and waves. Through this synthesis, he explored the origins of time, the evolution of the universe, and the principles that guide all existence. Consider the fate of the universe. Observations reveal that galaxies are receding, the universe is expanding, and this expansion is accelerating due to dark energy. What does this mean for the distant future? Stars will burn out, galaxies will drift apart, black holes will evaporate, and matter itself may decay. The universe may reach a state of quiet, dark emptiness, a heat death where time continues, but nothing changes. Yet even in this distant and stark vision, Hawking found fascination. Understanding the universe's trajectory is part of our journey as thinking beings. It is not despair that science provides, but clarity, perspective, and the awe-inspiring knowledge that the universe operates according to patterns we can comprehend. Throughout his life, Hawking emphasized one principle: curiosity. Every question, no matter how abstract, drives discovery. From the simplest observation of starlight to the most complex equations describing singularities, human curiosity is the engine of understanding. Hawking's life demonstrates that intellectual pursuit, persistence, and imagination are more powerful than circumstance. The universe is a narrative. Every star, every black hole, every quark tells a part of this story. And in this narrative, humans have a unique role. We are observers, interpreters, and participants. By asking questions about time, matter, and existence, we become part of the cosmos we study. Hawking's legacy extends beyond equations. It is a philosophy. The universe is intelligible, and knowledge is accessible. Science is not confined to laboratories or textbooks. It belongs to anyone willing to wonder, explore, and question. In a cosmos that seems indifferent, our curiosity imbues meaning. Even as Hawking faced physical limitations, his mind soared across galaxies and through the mathematics of reality. He turned disability into perspective, demonstrating that the limits of the body do not constrain the imagination. His voice, initially verbal, became digital, yet it communicated ideas that transcended words. In reading Hawking, we are reminded that understanding is both a challenge and a joy. Concepts like space-time, black holes, singularities, and quantum uncertainty are difficult, but they are also beautiful. They reveal a universe that is at once comprehensible and mysterious, finite and boundless, structured and unpredictable. As we conclude this part of the journey, consider the message Hawking imparted. The universe is ours to explore. We may not control the stars, bend space-time, or witness the Big Bang directly, but we can understand. We can study, analyze, imagine, and explain. We can participate in the unfolding story of existence. And perhaps most importantly, we can do so with humility and wonder. For every answer Hawking provided, new questions arise. The universe never stops inviting us to look deeper, think harder, and marvel at the vastness of reality. In the final part of this audiobook-style journey, we will reflect on Hawking's overarching vision, the unity of physics, the role of humanity in the cosmos, and the meaning we can draw from a universe governed by natural law. We will explore the culmination of his insights and the inspiration that his life and work continue to offer to every mind willing to dream. Stephen Hawking once said, "Remember to look up at the stars and not down at your feet." It is a simple phrase, yet within it lies the essence of his life, his work, and his philosophy. To him, the universe was not just a collection of matter and energy. It was a story waiting to be understood, a puzzle to be solved, and a source of inspiration for anyone willing to explore. Cool. By now, we have journeyed through the origins of the universe, the birth of atoms, the formation of stars and galaxies, and the extremes of black holes and singularities. We have walked through the interplay of relativity and quantum mechanics, and seen how these seemingly separate realms connect in the quest to comprehend the cosmos. We have explored time, space, and matter, always guided by the thread of curiosity that runs through human history. Hawking's vision extends beyond equations and theories. It is about perspective. In a universe that stretches billions of light years in every direction, our tiny planet may seem insignificant. Yet it is here that we think, wonder, and seek understanding. We are a part of the cosmos that studies itself, capable of reflection and insight. This, Hawking suggested, is a profound responsibility and privilege. Science, according to Hawking, is not cold or impersonal. It is deeply human. It allows us to see beyond our immediate surroundings, to understand the forces that shape the stars, the planets, and the very atoms in our bodies. It allows us to connect our existence to the larger universe, to appreciate the balance, the precision, and the astonishing improbability of life. Hawking also believed that our understanding of the universe could guide our future. By exploring the cosmos, we learn to protect our fragile world, to cherish knowledge, and to embrace curiosity. The universe, he implied, is not indifferent to us in purpose, but it does demand our attention, our effort, and our imagination. Consider black holes again. These objects, once thought to be destroyers, teach us about persistence, about information, about the resilience of nature. Consider the Big Bang. It reminds us that beginnings are not always visible, that creation is sometimes hidden behind a veil of complexity, waiting to be uncovered by those who look closely. And consider quantum mechanics. It tells us that uncertainty is not a limitation, but a feature of reality, inviting creativity, exploration, and the possibility of discovery. Hawking's insights bridge science and philosophy, connecting the physical universe with questions of meaning. He did not claim to have all the answers, but he offered a framework in which inquiry is endless and understanding grows with effort. For every mystery solved, new questions arise. This is not discouragement. It is an invitation to think, to learn, and to explore without fear. His life exemplified this approach. Confronted with a degenerative disease, he did not retreat from the universe, but engaged with it more intensely. He used his mind to reach the farthest corners of theoretical physics, and in doing so, he inspired millions. His courage, intellect, and humor demonstrate that limitations in one area do not preclude greatness in another. In studying Hawking's work, we also come to appreciate the beauty of simplicity. Concepts like the curvature of space-time, the evaporation of black holes, or the nature of time itself are complex. But Hawking presented them in ways that could be grasped, discussed, and shared. This accessibility is part of his genius. He believed that knowledge should not be hoarded, but communicated, nurtured, and spread. As we close this journey, consider the perspective he offers. The universe is vast, mysterious, and governed by natural law. Humanity is small, but capable of understanding. Life is fleeting, but remarkable. Knowledge is our tool, curiosity our compass, and wonder our guide. We have seen the universe evolve from a dense singularity to a vast cosmic tapestry of galaxies, stars, and planets. We have observed the forces of gravity, the dynamics of quantum mechanics, and the subtle influences that shape all matter. We have glimpsed the mysteries of black holes, the nature of time, and the intricate dance of particles and energy that underpin existence. Through it all, the thread of inquiry and exploration guides us, just as it guided Hawking. Hawking's legacy is more than scientific. It is a philosophy of engagement, to question boldly, to seek knowledge persistently, and to remain in awe of the universe. It is a reminder that understanding the cosmos can deepen our appreciation for life, inspire innovation, and elevate the human spirit. And so, as you reflect on this journey, remember the universe is not simply a backdrop for life. It is an intricate narrative in which we are participants. Our curiosity, creativity, and courage allow us to glimpse the sublime, to uncover hidden truths, and to share in the story of existence. Stephen Hawking's message is enduring. Look up, wonder, explore, and never stop asking the great questions. The universe will continue to expand. Time will continue to flow. Stars will continue to shine. And the human quest for understanding will continue. In our search for answers, we find not only knowledge, but connection, purpose, and the joy of discovery. This concludes our journey through Asterisk, A Brief History of Time Asterisk. But the story of the universe, and of our exploration within it, is far from over. Every observer, every thinker, and every dreamer carries forward the work of curiosity. The questions remain. What lies beyond the observable universe? What mysteries await in the quantum depths? How will our understanding of time, space, and matter evolve in the centuries to come? The answers are not yet known, and perhaps that is the greatest gift. For in the pursuit of knowledge, in the exploration of the cosmos, in the wonder of existence, we participate in the most remarkable story ever told, the story of the universe itself. So, look up at the stars, wonder, explore, and remember that the universe is vast, astonishing, and waiting for those who dare to understand it.